This is, I'm a seismologist by training. I've never been to a peer meeting, but I really appreciate the invitation to come here and learn what you all are doing. And I'm very interested in how you as users might consume the ground motions that we're calculating with our high performance computing simulations. This is a big topic. I didn't come up with this title. Carrie suggested it, but it's a bold a title, and it's a big topic. So I might be moving kind of quickly through here, so I'll try to move quickly though and try to cover everything. I want to acknowledge my coworkers. This is a multidisciplinary topic. We have a great team that involves applied mathematicians, computational computer scientists, geophysicists and seismologists, earthquake engineers, end users, and none of this work would be possible without the access to high-performance computing facilities at the DOE National Labs. I'll talk a bit about why I think this is an important topic. I think earthquake ground motion simulation is going to be a growing need for the earthquake engineering community. I think we've seen some examples of that today where people are using simulations. I think we'll be able to make more and more realistic simulations easier through improvements in methods and computing facilities. So I think there's a bright future for this topic. I'll talk a bit about the simulation methods and really focus in on the fact that high performance computing is needed to do the large scale simulations that are most realistic and of use for this application. I'll talk about some of the challenges that we face to have more realistic and useful ground motion simulations, and there are computational and physical challenges there. And I'll talk about some work on the Hayward Fault. We've done a lot of simulations on the Hayward Fault, which is the surface expression is just 2 blocks up the hill. We're right on top of it here in Berkeley, and I'll show you some recent results with that. Oh, and if you're local, I'm giving a talk at Berkeley Seismic Lab just down the hill. I'm lucky to spend some time there, and you'll hear a longer version of that if you're around next Tuesday. So we know that the empirical data is limited for large earthquakes at close distance, and that's where the damage is really key. It's most prevalent. And we also know that ground motions are highly variable due to the vagaries of ground motion and the earthquake process, stress drop, wave propagation, side effects, et cetera. And near fault ground motions are especially highly variable. They're shaped by the details of the earthquake source, rise time, stress drop, rupture speed, deactivity, is it rupturing at you, towards you? There is the generation of displacement, steps and velocity pulses that are so important for structural analysis. And the coupling of that ground motion from the source into the 3D Earth, particularly sedimentary basins, is key for generating long duration motions, and that can cause damage far from the source. And sometimes we have to be near the fault, and here we are right on top of the fault as an example. And of course, all of our critical infrastructure, our transportation, lifelines, water, everything has to cross the fault. An outline of what we're doing is running these large regional scale 3D simulations, generating ground motions on a grid, and they can be used to look at how structures respond in a nonlinear fiber type finite element modeling or in a coupled soil structure interaction. And Dave McCallan, who leads our effort in the DOE Exascale Computing Project, I believe will touch on this tomorrow, but that's an example of the use. The history of ground motion simulations, they've evolved as computational methods have improved. Early methods could run on a laptop computer today, but they lack a lot of the detailed, especially the 3D wave propagation effects that accounts for sedimentary basins and the known 3D geology and topography of the Earth. Our methods are really these kinematic ruptures in 3D Earth models where we're not appealing to stochastic methods to complete the high frequency component. We're running everything physics-based. We introduce the rupture, propagate those waves through time and as they move through the 3D Earth. There are other methods that include even more physics, rupture dynamics, and nonlinear geomechanics. They would be more detailed physics, but they have the inconvenience of having a lot of poorly constrained or unconstrained parameters that need to be specified. So for all these numerical methods, for then the 3D Earth, they require a certain number of points per wavelength, and it's expensive to double the wavelength. We have to decrease the grid spacing in the X, Y, and Z direction, so 8 times more points. We have to run it for twice as many time steps, so it's a factor of 16 computationally to double the frequency. We can improve on this by having mesh refinement, which we have in SW4, where the wave speeds, the grid spacing gets deeper with depth as the wave speeds increase, and that improves efficiency. If we look through time, at the maximum resolved frequency we've been able to achieve as a function of, say, the number of points on the y-axis or the total memory needed, right? The memory is going up and to the right as computers get faster and more powerful. In the last decade, we were running a billion-point simulation for 1.5 hertz or so, and we've improved that. This black line, or the solid line, is for the number of points that are required for a regional scale. That's 120 by 80 by 30 Bay Area Hayward Fault simulation. This is the number of points for a uniform grid. We jump down to this dashed line if we use mesh refinement, which reduces the number of points by a factor of 6, which is significant. So it shows that as we've added mesh refinement for the whole code, we can actually use less resources than we needed a while ago running uniform mesh, and it resolved higher frequencies. And if we've gone up here now, I'll show some results for a 10 hertz simulation that we ran on some of the most powerful computers in the world, the Summit and Sierra. If we had the luxury of having access to all of Summit and Sierra, we could run a trillion-point simulation and resolve 16 hertz. And that's all assuming we have a minimum shear wave speed of 500 meters per second, and it's all linear anelastic Q for attenuation. Okay, so on to the challenges. In the past, high-performance computers were clusters of networked CPU-based nodes. They communicated with message processing or message passing interface. They later started to pack more cores onto a node, so you could then take advantage of shared memory and use multi-threading, which improved efficiency. Computers now are using graphics processing units to offload the computationally intensive inner loops that we have in finite difference methods or other methods. And the software needs to adapt and be able to take advantage of that. A GPU is nothing. A node on a GPU machine has CPUs that manage the input and output in the direction of the work. But when they get to that intensive inner loop, we can say, okay, send that work off to a GPU, which is nothing but a cluster of many cores packed onto a card, so you can, in a single time step, do large array operations. There are challenges in the source modeling. Lots been learned. As we go to higher frequency, we expose problems with the source, right? We have to refine our source models because we find we get crazy results. We get large accelerations, say. And the feedback from engineering has been really important on that point. My colleague Arvind Pitarka, next door at my office in Livermore, is doing Rupture Dynamics, and this is informing some of what we know about earthquake rupture dynamics and tying that to observations. We find that there's longer duration slip in the shallow crust because of weaker confining stresses and weaker materials. The duration gets shorter for a given slip as we go down into the earth, and in an asperity we can have very large short duration pulses which then control the high frequency at depth. There are challenges in the path, and for this we really need to improve knowledge of the three-dimensional crust. Right, the waves that are generated at the source along a finite crustal fault from, say, 15 kilometers depth all the way up to the surface, all the way to the site, that whole part of the Earth participates in shaping the waves that we observe in our ground motions. And improving the 3D models is a big challenge. Our limited knowledge of 3D structure limits the validity of our models. A lot of models are based on ad hoc geologic and geophysical data. They're dense in some places and sparse in others, and we have to interpolate. There are seismic tomography results that fit travel times and surface wave dispersion and other things, but they don't fit waveforms, and that's what we need to fit if we're going to calculate these waveforms. Waveform-based inversion methods, full waveform inversion or adjoint tomography, promises to provide more well-resolved 3D crustal structure. And Carl Tape, in his thesis work at Caltech 10 years ago, showed this in Southern California, and that's something we'd like to do in the Bay Area and other places. Another challenge is really looking at path and site effects through improved geomechanics. We know that the Earth is not a linear elastic solid with linear anelasticity. There are, at high ground motion levels, for weak materials, there's plasticity and other nonlinear effects. And that's going to impact the large motions in the fault zone, right next to the rupture, and at the surface when we have those lower confining pressures. One way to handle that is to develop a code that includes all those 3D effects of plasticity. And the Southern California, or the San Diego State University group, Daniel Rattan and Steve Day and co-workers have put that in their finite difference code. And this just shows the plastic deformation for hard rock getting to poor quality rock. And you can see the amount of plastic deformation increases for poor quality rock on the fault zone. Another approach is to use a domain reduction method following Jacobo Bielek and co-workers, where we could run a regional scale simulation and then introduce the motions on the edge of a boundary that includes more complicated, possibly nonlinear geomechanics, plasticity, complicated structure, and even the structures, so you could do the full coupled soil structure interaction problem. All right, I'll move on to what we're doing in the Bay Area here for the Hayward Fault. We've simulated this 120 by 80 kilometer area with a magnitude 7 earthquake, 77 kilometers long. With SW4, it's a fully 3D finite difference code that includes surface topography, attenuation. It has mesh refinement. In order to generate motions that are of use to this community, 5 to 10 hertz or so, we have to have very fine discretization. Many grid points would fit in this room with sort of 12 to 6 meter grid spacing. And to run these calculations, we need enough memory to fit it on a large high-performance computing system. And most recently, the porting of SW4 to run on GPU systems has been a great achievement. So our goal is to calculate fully broadband, fully deterministic ground motions by introducing a kinematic rupture model. This shows a slip on the fault. That's then projected into a 3D model that includes the lateral variations of the seismic wave speeds, density, and quality factors. We put that into SW4. We run it on high-performance computing. And our workflows are now informed with, or are now done with, with Python. A few years ago, I bit the bullet, and I learned Fortran 77 as a graduate student, and now our workflow is really made possible with Python to set up the inputs, to keep track of all the data that we generate, and we still could improve that, but it's been a big help. All right. So porting to GPUs has been great. A few years ago, we ran a calculation on all of Cori during a maintenance period. This is a machine just up the hill at LBL. It used 85% of the machine to resolve 0 to 5 hertz on the Hayward Fault. And we wrote a paper on this one single calculation. Meanwhile, we were working at Livermore to get codes running faster on the anticipated GPU architectures that came online in 2018. And we were able to run that same calculation on 6% of the Sierra machine. It's now a routine calculation on Lassen, Sierra's little brother. And I've done 50 of those calculations resolved to 5 hertz. So it really opens up a new set of possibilities. We get a 50x speed up in terms of core hours. And two codes, it's one code running on either a CPU or GPU, and we get identical results, so they're verified. So this greatly facilitates the code management. I won't be able to get into that but there is a significant computer science effort. As we resolve motions to higher frequency, here's a site in Livermore, fault parallel, normal, and vertical. This is a calculation resolved to 1.25 hertz, 2.5, 5, and 10 hertz. You can see the high amplitudes increase as we resolve higher frequencies because we're resolving those high frequencies that control PGA. But the longer period surface waves generated by the basin structure there, they're well resolved at 1 hertz. If you're interested in tall buildings and large structures, maybe 1 hertz is good enough for you. We can do hundreds of those calculations today in a weekend. But if you're interested in the broadband, fully deterministic, it's more challenging. So each doubling of the frequency is a factor of 16 harder to run that calculation. So this is a factor of 4,000 harder to do 10 hertz than it is to do 1.25 hertz. We compare our ground motions with GMPEs from the Pier NGA West 2. This is a reference here is the average of 4 NGA West 2 calculations for 2,300 sites across the Bay Area. This is epsilon. I shouldn't have to explain to you what that means, but I know what it means now because I took Norm's class. It is the median. The median values are near zero, and 50% of the data is shown as the gray. And you can see that across this band from PGA, PGV, spectral acceleration at 10, 1, 10 hertz, and 100 hertz are well resolved. In fact, you can see we're relatively unbiased even for the Fourier components that are not resolved in the calculation, spectral acceleration at 1 hertz. So one of the shortcomings that we have is we run a calculation, we have to choose a minimum shear wave speed. And if we choose it too low to try to match what's actually out there, then that's going to limit how high frequency we can go to. We often, commonly we choose 500 meters per second, which is sort of a stiff soil. And we know that's a shortcoming, and we know the Earth does not respond as a linear elastic solid when you hit it with 1g acceleration. There's a new Fourier spectrum-based ground motion model, another peer project by Jeff Bayless's thesis work with Norm. This allows us to form a transfer function, so I can divide out the response, the Fourier amplitude response, for a linear response with a minimum shear wave speed of 500 or a VS30 of 500. And the numerator then includes the response for a lower in situ shear wave speed that includes linear and nonlinear response. That transfer function is plotted for a site in Berkeley here that is subjected to about half a G PGA. It's 2 kilometers from the fault with a VS30 of 110 meters per second. So the dashed line is the response just for the linear part that basically says, hey, you need to amplify because you're in a soft soil. But the black line includes the nonlinear term, which says, hey, we need to reduce that amplitude because you're gone nonlinear. When we do that, we go from the output of SW4 for the horizontal components is shown as black. The green is after we've applied the corrections. In Fourier amplitude space, this is the black line, the output of SW4. It has too high of high frequency and not enough low frequency. When we apply the transfer function, we get something that's closer in line. So lastly, I just want to make a few comments about calculations. Moore's law tells us that, right, computers just get faster and faster. We have evidence of that with the IEEE's, top 100. They get faster and faster every year, and they keep allowing us to make great progress in all of the science and engineering that we do. Technology companies anticipate this change, and someone this morning mentioned that, we don't know always how we're going to use the new systems, but we know they're coming. And I would argue that future methods in seismic hazard and risk should rely on physics-based 3D simulations to provide ground motions for structural engineering response and performance-based design, geotechnical response. You know it's coming, so we should be talking now how we can use it. So I'm very interested to talk with people. I'll be around today and tomorrow who are, I'm interested to hear how you might consume the calculations that we're able to generate, or what are the specific scenarios or cases that are of interest for your engineering problems. So to summarize, there are 3 factors that really make these calculations accessible: improvements in methods and algorithms. Computers just keep getting faster and more powerful, and we need to optimize our codes to run on those platforms as they become available. And three elements we really need to keep our eye on so that we're, as seismologists, generating ground motions that are realistic. That is the rupture models, make sure we understand the slip functions and rise times, and as we push to higher frequencies, follow the developments in rupture dynamics, make sure our rupture models are realistic. We need to improve 3D crustal structure. And there's methods to account for geotechnical structure. And I'll stop there. Thank you.